Good afternoon. Good afternoon. Today, we are talking about the contingency table, right? Contingency table. We talked about the t-test, the z-test, a lot of the method. Contingency table, very interesting. If you talk to the practitioners, many of those practitioners, medical doctors, scientists, they know this contingency table very well, but I thought it's worth to talk about. I started with one example. Regional difference in the United States, right? See, Northeast, where we are, compared to the West, like California, all those. Question is a different region. The high school graduating rates are same or different, statistical different. In other words, the region, the location, is it related to the high school graduating rates? Here's the data. We select a sample, right? Now you see in the Northeast region, 1,313 people, about over 1,070 graduated from high school. West region, in the sample, 2,675, about 2,079 graduated from the high school. Well, from the real data, probably you don't have much sense, all right? Let's see now if you see the proportion. Now you see the difference, right? You see the difference. You see, oh, Northeast region, in terms of percentage, high school graduating rates, 81.5%. West only about 78, 77.7. It's obviously Northeast region, our region, is better, right? It's better. Wonderful. You have wonderful mathematics knowledge, 81.5, greater than 77.7. Wonderful. Well, this percentage from samples. What we really want to know is to population, huge population. The people in the Northeast region compared with the people in the West region. As we learned in the previous several chapters, the sample difference tells us something, but not necessarily 100% reflect the population difference. Why? The randomness of the sample. So here's the dilemma. On the one hand, well, hey, Northeast region has high school graduating rates, right? Than West region from the sample. Is this sample information significantly different? This difference, is it statistically significant? Or, well, may caused by the randomness of the sample. Now we need to run the contingency table and learned one method called chi-square, right? Chi-square, chi-square. Here's a definition. When you see the example, you will understand the definition much better, right? The so-called two-way frequency tables, right? Continuous table. And you really have the two variables. One variable is used to categorize rows, and the variable is used to categorize the column. Like our example, one variable, graduated from high school or not, right? Another variable is about the location, the region. Test of the independence. What we are going to test? We are going to test of independence. We're wondering, is location matters regarding the high school graduation rates? Or doesn't matter, right? This is a wonderful country, everybody's saying, so is location where you live, say in northeast region or west, matters? That is what we're going to test, right? To test. Here's a bunch of the symbols. O represent observed frequency, how many? But really in the sample. This E represents the expected frequency. Well, some of you may say, oh, what do you mean? Expected frequency? I will talk more in detail. R, numbers of row, right? And the C, numbers of the column. That's easy. Here's one. The formula to calculate the chi-square, and the formula to calculate the so-called expected value for each cell. What that means, we will back to the formula later, right? Let's see here. Let's do the one. This is what we observed really from the sample. 1,070 people graduating from the high school in the northeast region. What it means, expect the numbers of the students graduating from high school. What that means and how we calculate. We calculate this is quite simple. The row total times the column total and divide by the grand total. You're back to there. You see, you want to calculate the expected number of the people graduated from the high school. You see A in this column total 3,149. That column, sorry, this row is 3,149, and the column total 1,313, and the grand total 3,988. So it's so easy to calculate, right? You have this formula. Come out like 1,036. Oh, well, should I say 37 people, right? Same thing, you can calculate the expected value for other cells. All right. So the fundamental question here is, what are those expected value really meant? Those expected value, right, so-called expected, is under the important assumption people say, hey, location does not matter regarding high school graduating rate. No matter where you live, right? The chance you're going to graduate from the high school is the same. Under that assumption, in other words, North, the East region, and the West region, they have the same high school graduating rates. Under this assumption, we would expect, in this case, like how many students graduate from the high school in the Northeast region, right, from this sample, and how many not graduate, how many graduate the red one from high school in the West region, and how many not. Under that assumption, the location does not matter. We have those so-called expected values. Well, tricky. You see, what we expected is not the same as what we really observed. There's a difference. There's a difference. There's some relative small difference, all right? In this case, it's quite a difference. What's wrong? Why what we expected, we think it should be, is different than what we really observed in our sample. Some of you say, hey, maybe we made the wrong calculation, right? Our calculated battery was dead or something. Everything fine. Everything fine. We follow the right formula, right procedure. So why there is such a difference? Oh, the fundamental assumption, which says location has nothing to do with the high school graduating rate, right? That fundamental assumption was probably wrong, was very likely was wrong. Well, some of you may still arguing, say, hey, professor, I see the difference. But as you said, the sample has its randomness, right? Is this difference caused by the sample randomness? Or really, as you said, kind of caused by the population difference in terms of high school graduating rate? Very good question. That's why we needed to quantify those difference and trying to make the decision based on what is really the difference it is, right? See, this is a chi-square calculation. We so-called test statistic. So you do this. This is the difference between expected or should be, right, and what we really observed. The square just makes all those difference is like the positive measurement. You don't want to like cancel out. And divide by expected value to standardize the measurements, right? Finally, you add all those together for all the cells, come out 7.562. One last question. You see, hey, 7.562, is it large or big enough, this difference, and make us to conclude the Nye hypothesis, right? Which was to say, hey, location doesn't matter, right? Was wrong, be rejected, right? So this is something, as we've done many times before, we have to calculate the p-value. Using the technology, well, old days is table, but these days always software, R, StairCrunch, whatever, you know those, and even the Excel, right? You can calculate the p-value, which is so small. When the p-value is so small, in this case, definitely less than our R, 5%, right? So we reject the Nye hypothesis and support the alternative hypothesis. Support alternative hypothesis. Yeah. You see, back to there, what was the Nye hypothesis H0? Nye hypothesis was the location and the high school graduating rate are independent. Doesn't matter where you live. It's competing alternative hypothesis. The location and the high school graduating rate are dependent. Now, because the p-value is so small, definitely less than alpha. So we reject the H0, as we done many exercises before, right? We reject the H0, so we support the alternative hypothesis, H1. All right, so now we can conclude. High school graduation rate really related to the location where you live, right? Northeast or west region. Have a wonderful day. Have a wonderful day. It's kind of short, but have a wonderful day. Really, really my pleasure. Thank you.